In this video, we're going to talk about stoichiometry. These are your learning targets. If you need more time, go ahead and pause the video. And remember, you can pause the video whenever you want. So stoichiometry is a study of quantitative relationships. And remember what quantitative means, right? It's about numbers. So we're talking about a numerical relationship between the amount of reactants and the amount of product. This concept is based on the law of conservation of mass. Now, this comes from the law of conservation of matter that we learned previously. And remember that the conservation of matter states that matter is neither created nor destroyed. So what you start with in your reactants, you need to have in your product. For example, if you have hydrogen and oxygen that you begin with, you will have hydrogen and oxygen at the end of your reaction. So we know that as a chemical reaction is going on, the chemical bonds between these atoms are breaking and new ones are forming, and that's how we get different product. And so remember that the atoms are just simply rearranging, right? So what we have in the beginning should be the same as the end in terms of the number of atoms and the types of elements. And so the law of conservation of mass states that the mass of the reactants equals the mass of the product. So if we take a look at this example, we have iron and oxygen that yields iron 3 oxide. Remember, on the left side of the arrow is where we have the reactants. On the right side is where we have product. When we balance it, we have the coefficients 4, 3, and 2. And using words that we used previously, we know that this represents 4 iron atoms, 3 oxygen molecules, because remember they're diatomic, and 2 iron 3 oxide formula units because Fe2O3 is an ionic compound. Now, the new thing here is that the coefficients also represents moles. So we can say 4 moles of iron, 3 moles of oxygen, and 2 moles of iron 3 oxide. So the first problem on your worksheet says, determine the masses of iron, oxygen, and iron 3 oxide based on the balanced reaction above. So what we're going to do is we are going to start with the number of moles of each substance. So for example, starting with iron, we are beginning with 4 moles of iron, and we're going to set it up like a fence. And remember what we do with the fence, right? First you want to, you get a pen here. First you want to copy down the like unit. Okay, so remember we're kind of ignoring the number, and we're going to take the unit and bring it down, and we're just copying it, right? And so we have moles of iron written down. On top, because we want to get to mass, we're going to go ahead and write grams of Fe. So what is this, and where do I get this information? This is molar mass, right? So how do we get the molar mass? We are going to look on our periodic table. And for this example, we're going to look at iron. Okay, now remember this is in your Google Classroom where it says periodic table if you lost your own copy. So we're looking at iron, and we have 55.847 grams per mole, and we're going to be consistent, so we want to round it to the 100th place, 2 decimals after the 2 places after the decimal place. So 55.85 is what we're going to use. So remember that is 55.85 grams of iron is equal to 1 mole of iron, so you want to make sure you're putting the numbers in the right place. So we write 55.85 next to grams and 1 next to mole. You can go ahead and multiply, right, and then divide by whatever's on the bottom, and that's over 1. Your like units cancel out, and we get 223.40 grams of iron. Now make sure that you're pausing this video and you're trying this out with your calculator, right? Don't just assume that my answers are correct, and plus I want you to practice this just like we did in class. So the next one, we're going to start with 3 moles of oxygen. Again, copy down your unit. We have the molar mass of O2, not just O, so look at the formula. It says O2, so we want to do 16 times 2. So 16 grams is usually what 1 oxygen is, but because there's O2, we want to multiply that by 2, and we get a total of 96 grams. I'm going to do that for the last one, 2 moles of iron 3 oxide. Copy down the unit, and the mass of iron 3 oxide is 159.70 grams. Multiply that, and you get 319.40 grams. All right, so the second part of this problem says determine the total mass of the reactants and then the total mass of the product based on the balanced reaction below. Well, we figured out all the masses, right? So for 4 moles of iron, we have a total of 223.40. 3 moles of oxygen is 96 grams. And 2 moles of Fe2O3 is a total of 319.40 grams. So now we want to take this separately. We want to look at the reactant separate from the product. So this is the reactant, right? Whatever's to the left of the arrow. There are our reactants, and then to the right of the arrow, there's our product. So we want to add up the total mass of the reactants because we have 2 different reactants, right? So we add it up and we get a total of 319.40 grams. We don't need to do anything for the product because there's only 1 substance for the product. So what do you notice about these 2 masses? Right, they're equal. So the mass of the reactants equals the mass of the product. We just proved the law of conservation of mass. So because of the law of conservation of mass, we can actually predict how much product is going to be produced based on how much reactant we begin with. Or we can predict how much reactant we need of one substance if we have X amount of another reactant. And that is what stoichiometry is. So when we do these problems, you're going to see that I'll be using this kind of pathway or guideline. So we have particles of A or grams of A. They're going to start in the same position, and it's going to go into moles of A, it'll go into moles of B, and then it'll go back out to particles or grams of B. So A, in this case, is your given substance. B is your desired substance. So these 2 will be your starting points. Okay, so you can start here or you might start here. These 2 are your endpoints. So you might stop at moles or you might go all the way to grams. Okay, it depends on the problem. Oops. So let's take a look at the first example. To produce 12 moles of water, how many moles of oxygen gas are needed? The first thing that you should do, or that I suggest, is you write down what is given and what they want. So we're going to do that in using our balanced reaction that's given right here. Okay, so they give us 12 moles of water, and I'm going to write that under this water right here. And they want moles of oxygen, so I'm going to write that over here. Now everything else we're going to actually ignore. So you can cross it out. Even though it's important to the overall balance reaction for this particular problem, we're not going to look at that anymore. So now I'm going to pull up the picture that I was talking about previously, and I want to match up my starting unit. Okay, so remember that it is giving us 12 moles of water, so that's where we're starting. Okay, so I'm going to go ahead and cover up my first picture because I don't need that. Okay, so I'm going to write 12 moles of water. And the next thing I'm going to do is I'm actually going to look at the next part. So this tells us where to go next, and it says moles of B. Well, what is B in this case? B is what it wants of O2. Okay, so I'm going to write moles of O2 right underneath it. Okay, I'm going to go ahead and cover up the other part because it's not asking for grams and it's not asking for particles. Now, the beauty of this path is that it tells you, or it gives you, the upper part of your fence setup. So we're going to go ahead and replace the arrow with the fence, and then you guys know what to do on the bottom part, we are simply going to just copy that unit down into our fence, right? So we write moles of water. Now this here is called a mole ratio. Now we've never seen this before. This is moles of one substance over moles of another. Previously what we've seen is moles over G, or G over mole, or particles over mole, or a mole over particles. We've never seen moles over moles. And so when you see this, this is called a mole ratio. And where do we get the mole ratio? Well, we're actually looking at the coefficients, okay? So the coefficients, remember, like we talked about in the beginning of this video, it tells us, another way to say it is, it's the number of moles of a substance. So for example, this is 7 moles of oxygen, and this is 6 moles of water. And you're going to go ahead and match up that number to the unit in your fence. So 6 moles of water, right? And then 7 moles of oxygen, okay? And then we solve. Like units cancel out, which in this case is moles of water. Go ahead and multiply across, divide by whatever's on the bottom. In this case it's 6. And we get a total of 14 moles of oxygen. Number 2, when copper reacts with silver nitrate, according to the equation, what will be the number of grams of copper required to produce 432 grams of silver? So what are they giving you? They are giving you 432 grams of silver. So again, write that underneath the balance reaction. What do they want? They want the number of grams of copper. So again, everything else, ignore, and in this case, I'm just going to simply cross it out. Okay, so I'm going to bring up the picture that I talked about in the beginning of the video. All right, so in this case, we want to go ahead and match up our grams. This is our given. So we want to start from the beginning, right? So we want to match it up with that one. So we're going to write 432 grams of silver, and this is our starting point. Okay, so now what is next in our picture? Next is moles of A. So in this case, what is A? A is silver. So that's the same thing that we're writing, moles of silver. And we keep going. Now the next thing says moles of B. Now, what is B? What are we trying to find? We're trying to find copper. So we're going to go ahead and write, we're going to copy down that word moles, and we're going to write copper. Now, we have one more step, right? This is grams. We got to match it up to the unit. So there's grams. So we're going to write grams of copper. So this, again, gives you the top part of your setup. We're going to go ahead and replace the arrows, or you go ahead and erase it on your paper, and we're going to draw the fence. Simple as that. Okay, so again, what do we do on the bottom? We just copy down the previous unit, right? So if this is grams of G, or grams of silver, we're going to bring down grams of silver. Moles of silver, moles of silver. Moles of copper, right? Notice I don't write any of the numbers, okay? Except for the beginning, because that's our given. All right, so now let's take a look at each fence. So let's take a look at this one right here. Mole over G. Well, we've seen that before, right? What is that? That is molar mass. Where do we get molar mass from? We've got to use the periodic table, right? So find silver on your periodic table. Remember, whatever mass is on the periodic table, that is all equal to 1 mole. So in silver's case, we have 1 mole is equal to 107.87 grams. Okay? Now, what's this next fence? Moles of copper over moles of silver. Remember what I said about moles over moles? That's called a mole ratio, right? So where are we looking for the mole ratio? We are looking at the coefficients up top, right? So silver has a coefficient of 2 moles of silver. What about copper? Copper doesn't have anything, but what are you assuming if there's no number in front? Right, there's a 1 in front, right? So 1 mole of copper to 2 moles of silver. So make sure you're writing the numbers in the right place. So we have 1 mole of copper on top, 2 moles of silver on the bottom, okay? Last fence. We have grams over moles. Grams of copper over moles of copper. What is that? Grams over moles, grams per mole. That is, again, another molar mass. Except for this time is for copper, right? So find copper on your periodic table. Okay. And then you should see that 1 mole of copper is equal to 63.55 grams. Okay, and then we go ahead and cancel out the like units. That way we end up with grams of copper, multiply across, divide by whatever's on the bottom. If you're using a TI calculator, make sure you guys are using parentheses, right? And you're getting an answer of 127 grams of copper. All right, last example. One of the main components of pearls is calcium carbonate. If pearls are put in acidic solution, they dissolve according to the equation below. How many grams of calcium carbonate can be dissolved in 0.0250 moles of hydrochloric of HCl? So what are they giving us? They're giving us 0.0250 moles of HCl. They want grams of calcium carbonate. Everything else, again, ignore. All right, so we're going to bring up our picture. And where do we want to start in this picture? We want to match it up, right? So if we're given 0.0250 moles, do we want to start at particles or grams? No, it doesn't match. We want to start at moles of A. Okay, so we're going to go ahead and ignore that. You can just cross it out on your paper. And I'm going to start with 0.025 moles of HCl. All right, so remember, where are we trying to go? Are we going to end at moles? Or what do they want? They want grams, right? So we got to go all the way to grams. So the next thing in our picture is from moles of A, we're going to go into moles of calcium carbonate, CaCO3. And then we want to do one more because it's asking for grams, so grams of calcium carbonate. So again, we just set up the most difficult part of our fence, right? We set up the top part. Let's go ahead and erase those arrows and make a fence. Go ahead and copy down the previous unit to the bottom of the fence. So moles of HCl, moles of HCl, moles of calcium carbonate, moles of calcium carbonate. And then let's figure out our mole ratio of calcium carbonate to HCl. Two moles of HCl to 1 mole of calcium carbonate. And grams over moles, remember that's another thing for molar mass. This one you're probably going to take a little bit more time trying to figure out the molar mass, so go ahead and pause the video so that you guys can do that on your own. You can practice doing the molar mass. Remember, it's calcium plus plus carbon plus oxygen. And how many oxygens are there? There's 3 of them, right? So calcium plus carbon plus oxygen, and remember to multiply the oxygen times 3, okay? So pause it here to get the molar mass. And you get that 1 mole of calcium carbonate is equal to 100.09 grams of calcium carbonate. Multiply through, divide, you get 1.25 grams of calcium carbonate, okay? So on your paper, you have 2 more example problems. I want you to try to do that on your own. You have answers on the bottom of your paper. The answers are given to you at the very bottom. Make sure it matches. I believe my answers are considering significant digits. Okay. So go ahead and pause the video here. I want you to do those 2 practice problems, and then when you're ready, go ahead and start it up again, and we'll talk about percent yield. So percent yield tells us how successful a reaction is in producing the desired product. It is the ratio of the actual yield to the theoretical yield expressed as a percent. So percent yield is equal to E over T, experimental yield divided by theoretical yield. So E over T sounds like percent error, right? It's not the same thing, okay? So percent error is talking about error, okay? Percent yield is talking about how successful our experiment actually was. So the theoretical yield is coming from our stoichiometric calculations, okay? So we can do the work and predict how much we're supposed to get out of our experiment, right? And then we compare it to what we actually got. So let's take a look at this problem. When potassium chromate is added to a solution containing silver nitrate, solid silver chromate is formed. From our calculations, the reaction should produce 0.488 grams of silver chromate. After doing this experiment, Sally obtained 0.455 grams of silver chromate. Calculate the percent yield. So if you're reading this problem, you can figure out the experimental yield and the theoretical yield. Both of them are given to you in the problem. So which one of these is experimental yield? Is it 0.488 grams or is it 0.455 grams? So remember, experimental yield is what you get from the experiment, right? So Sally got 0.455 grams, so that's her experimental yield. Doing her calculations, she predicted that she was going to produce 0.488 grams. There's your theoretical yield. So let's go ahead and write the formula. Percent yield is equal to E over T times 100. We're going to go ahead and plug it in. 0.455 divided by 0.488 times 100. And we're going to get, and time 0.488 times 100, and we're going to get a percent yield of 93.2%, which is really good, right? That's a high yield. She got 93% of what she was supposed to get, okay? The next problem is a two-part problem. It says calculate Jane's percent yield if she reacted 0.53 moles of potassium hydroxide and she produced 44 grams of potassium sulfate according to the reaction below. So they're giving us two numbers, 0.53 moles of potassium hydroxide and 44 grams of potassium sulfate. Well, what is her experimental yield? Right, she produced 44 grams of potassium sulfate, right? So that's her experimental yield. So then does that mean that 0.53 moles is our theoretical yield? No, it means that that's what she started with. So again, this is a two-part problem. You need to figure out her theoretical yield. How much was she supposed to produce given that she started with 0.53 moles of potassium hydroxide, right? So we're trying to find mass of potassium sulfate. We're going to go ahead and ignore the rest. I want you to go ahead and try setting up the fence starting with this time moles of A, right? And you're going straight through the picture. You're going to end at where? Grams of B. Go ahead and set up the fence and figure out her theoretical yield. Go ahead and pause the video now. And from your calculations, you should have gotten 46 grams, right? So theoretically, she was supposed to get 46 grams. She actually got 44 grams. Go ahead and plug it into the formula. Percent yield is equal to E over T times 100. What is her percent yield? %95.7%. She had a pretty good experiment. All right, and that's it for stoichiometry.